Hello, this is homework 10. In this homework session, we will be solving problems 1, 3, 8, 16, 24, and 39. Let's begin. Okay, problem 10-1 reads, in each case, both the force F and the rod lie in the plane of the page. The rod has length 4 meters. The force has magnitude 10 newtons. So L equals 4.00 meters, and F equals, well, that would be incorrect because we're just doing the magnitude here. So F equals 10 newtons. All right. Calculate the torque, magnitude, and direction about point O due to the force F in each of the cases sketched. So the first one, A, we have point O here, and we have a force going this way. This angle is 90. And so this is L equals R sine theta. And that's the lever arm. That equals 4 meters, 0.00 meters, times sine 90, which is actually 4 meters. L equals 4.00 meters. And then the torque is going to be 10 newtons, 10.0 newtons, times 4.00 meters. And that's going to be 40 newtons times meters. And that's going to be into the page, right? Because you have R this way and the force there. So it's turning. R cross L is going to be going around this way. And that would screw it into the page. So this is into the page. Okay, were we supposed to do direction 2? I reckon. Wait a minute. Wait. R cross F. 1 second. Oh, my bad. R cross F would bring it out of the page. That's unscrewing. Yeah, out of the page, not into the page. That would be the other way. So if it goes this way, counterclockwise, it's going to screw it out of the page. Okay. That. All right. That was 10.1a. 10.1b, we have a figure like this. So now we're going to figure out the lever arm. L equals R sine theta, or phi. I think they use phi. And that's going to be equal to 4.00 meters times sine of 120 degrees. So L is going to equal to 3.464 meters. T equals 10.0 newtons times 3.464 meters. And our magnitude is going to be 346 newtons times meters. And this again is going counterclockwise, which would bring it out of the page. So R cross F is out of the page. And it's going to look like that. (10.1c). This time we have something that looks like this. Once again, that's all of them are 4 meters, 4.00 meters. And we've got our force going this way. This is 30 degrees. Phi. So now we are going to calculate that lever arm. L equals 4.00 meters times sine 30. That's good. L is going to equal 2.00 meters. And torque is going to be 10.0 newtons times 2.00 meters. And that's going to be 20 newtons times meters. And this again will be out of the page. You've got R cross F, and it's out of the page. And that symbol's out of the page. Into the page, by the way, looks like that. 10D. We have a scenario like this, where the force is applied midway. So now we have the lever arm, R equals R sine V, equals 2.00 meters times sine 60, equals 1.732 meters. And the torque is going to equal to 10.0 newtons times 1.732 meters. That's going to be 17.3 newtons. And we are, this time, we're going clockwise, which is into the page. Into the page, 10D. Now, on this one, 10E, we have our force. The angle between our force is going to be 180 degrees. Phi equals 180 degrees, right? This is going this way, our force is going that way. So for our lever arm, L equals R sine phi, we're going to get nothing. Sine 80 is 0. So we're going to get 0. So there's no torque produced here. No torque. Okay, that was 10-1. This is 10-3. It reads a square metal plate, 0.180 meters on each side. Is pivoted about an axis through point 0. So it looks like this. That's 0. At its center and perpendicular to the plate. Calculate the net torque about this axis due to the 3 forces shown in the figure. If the magnitudes of the forces are F1 is 18.0 newtons. F1 is here. F2 is 26 newtons. And F3 is 14 newtons, and it's here at 45 degrees. Let's see. The plate and all forces are in the plane of the page. Okay, so we know this is 0. All these sides are 0.180 meters, and the lever arms are going to be here. So first of all, we need to find out, the radiuses are going to be there. We need to find the distance of that. So it's, if I take this, do the Pythagorean theorem, I'll get R, all the R's equal each other, equal square root of 0.09 meters squared plus 0.09 meters squared. And that will give me 0.1273 meters. So R is going to equal 0.1273 meters. Okay. All right, now we'll just start with 1, 2, and 3. So we need to find the lever arm for 1. L1 is going to be equal to R sine phi. And that's going to be equal to 0.1273 meters times sine 135. Let's see. Right, because this is 90. And this is 45. So it's going to be times sine 90 plus 45, which is 135. So L1 is going to be 0.0900 meters. T1, torque, tau 1, if you will, is going to be, we're going to use the convention that counterclockwise is positive and clockwise is negative, so negative 18.0 newtons times 0.900 meters is going to give us negative 1.62 Newton meters. Negative 1.62 newtons times meters. Lever arm for 2 is going to be L2 equals 0.1273 meters, again times sine 135, and that's going to be the same thing, 0.900 meters. And now tau 2 is going to be positive. The tau 2 is going to be plus 26 newtons times 0.09. Sorry, that's 0.09. 0.0900 meters. And that is going to give us plus 2.34 newtons. All right, finally 3. The lever arm for 3 is, this is going to be 90. So it's going to be L3 equals 0.1273 meters times sine of 90. And that's going to be 0.1273 meters. And tau 3 is going to be 14 newtons. It's going to be negative 14 newtons. Wait. Tau 3, that's going to be positive. It's going counterclockwise. Negative 14 times 0.1273 meters. And that's going to give us 1.78 Newton times meter. 1.78 newtons meters. Now, adding all these up, let me pause, get some board space. The sum of the torques is going to equal all the 3 various values added. And let's see, it's positive, so that means it's going this way, which that screws out of the page. Going to be out of the page. That's 10.3. 10.8 says a uniform disc with mass 40 kilograms and radius 0.2 meters is pivoted about its center, about a horizontal frictionless axle that is stationary. The disc is initially at rest, then a constant force of 30 newtons is applied tangent to the rim of the disc. A, what is the magnitude? B, of the tangential velocity of a point on the rim of the disc after the disc is turned through 0.200 revolutions. So delta theta equals 0.200 rev times 2 pi over 1 rev. And B, what is the magnitude A of the resultant acceleration of a point on the rim of the disk after the disk is turned through the same? So we want to find V and A. All right, the first thing we need to do is find the moment of inertia, which is going to be modeled after a cylinder. So I equals 1/2 mr squared. So I is going to be equal to 1/2 times 40 kilograms times 0.200 meters quantity squared. I equals 7.5 radian. Wait, I is going to be equal 0.800 kilograms per meter times meter squared. And now we'll solve for omega. So we'll use omega final squared equals omega initial squared plus 2 alpha delta theta. Oh, but we need to find alpha, don't we? All right, so F R equals I alpha. So F R over I equals alpha. All right, so we've got 30 newtons. 30 newtons, that's the force. Radius is 0.200 meters. And I is 0.800 kilograms times meters squared. So alpha is going to be 7.50 radians per second squared. All right, now to solve for omega, we know this guy is 0. So omega final squared equals 2 times 7.50 radians per second squared times this value. And that value is going to be 1 minute. Now the calculator, clear, 0.2 times 2 times 1.256 radians. 1.256 radians. All right. And now omega is going to equal to 0. Omega is 4.342 radians per second. Omega equals 4.342 radians per second. And let me get some board space. All right, continuing on. V equals R omega. So V is going to be equal to 0.200 meters times 4.342 radians per second. All right, V, put that in our list of values, is going to be equal to 0.868 meters per second. All right. Now to solve for A. A is going to be equal to the square root of A tangential squared plus A radial squared. So A tangential equals R alpha, which is going to be 0.200 meters times alpha, which was 7.5 radians per second squared, 7.50 radians per second squared. And that's going to be equal to 1.50 meters per second squared. And that's a tangential. A radial is going to be equal to R omega squared. And that's going to be equal to 0.200 meters times 4.342 radians per second squared. And that's going to be 3.77 meters per second squared. Now, take those values. A total equals the square root of 1.50 meters per second squared plus 3.77 meters per second squared, and you're going to get 4.06 meters per second squared. And that was 10.8. That's a good problem. 10.16 reads, a 12-kilogram box resting on a horizontal frictionless surface is attached to a 5-kilogram weight by a thin, light wire that passes over a frictionless pulley. The pulley has the shape of a uniform solid disc of mass 2 kilograms and diameter 0.500 meters. After the system is released, find A, the tension in the wire on both sides of the pulley, and B, the acceleration of the box, and C, the horizontal and vertical components of the force that the axle exerts on the pulley. All right, you got this guy. Here, the pulley and something hanging. Here's there. And this guy is 12 kgs. And this guy is 5 kgs. So we've got the sum of the forces in the X is going to be the, this is number 1, and that's number 2. So T1 equals M1A. Sum of the forces in the Y, this guy, M2G minus T2 equals M2A. And these tensions are going to be different because of the pulley is not massless. And it's so it's going to change the tensions on both sides. All right, and then for the pulley, we have T2 is going to be bigger than T1 minus T1 is going to be equal to R is going to be equal to 1/2 mR I alpha squared alpha. This is I. So TR equals I alpha. So this is the net torque times R equals I. This is I for a cylinder, a pulley, and that's alpha. Okay, now to, we don't want to deal with A's and alphas, so let's go ahead and change that. So A equals R alpha, right? So alpha equals A over R. Alpha equals A over R. So I'm going to go ahead and take one of these R's out already. So T2 minus T1 equals 1/2 MA, because I take the A over R substituted here, and the other R cancels, and I've got MA. So now I've got 3 expressions. Let me pause and clear up some board space. Okay, now I'm just going to add these three expressions starting, oops, there we go, starting with this guy. And I'm going to get, for over here, I'll put it here, M2G plus T1 minus T2 equals M1A plus M2A. All right, now if I add these guys and this and this will cancel, you see that? So those guys will go away and I'll get M2G equals M1A plus M2A plus 1/2 big M, the mass of the pulley, A. All right, now I got something I can work with. Fill all that in and solve for A. All right, A is going to be equal to M2G divided by M1 plus M2 plus 1/2 mass of the pulley. And if I put all those values in, I'm going to get 5 kgs times 9.8 meters per second squared divided by 12 kgs plus 5 kgs plus 1 kg. And that's going to be equal to, A is going to be equal, put it over here, equals 2.72 meters per second squared. All right, let me pause and get some board space again. All right, now I'm supposed to find the tension in the wire. So we have a T1 equals M1A. So what's M1 is 12 kilograms. T1 equals 12 kgs times 2.72 meters per second squared. And that's going to give me 32.6 newtons. And T2 is going to be equal to M2G minus M2A. So T2 is going to be equal to M2, which was 5 kilograms, 5 kgs times 9.8 meters per second squared minus 2.72 meters per second squared. And T2 is going to be equal to 35.4 newtons. Okay, that was a acceleration of the bob. We already have that, 2.7. And then the horizontal vertical component of the force that the axle exerts on the pulley. All right. Okay, as far as the horizontal and vertical components, forces on the pulley, we've got F of X is going to equal the tension and that horizontal T1. That's going to be 32.6 newtons. And Fy is going to be equal to T2 plus mg, right? That's going to be pulling on that axle. And so that's going to be equal to, T2 was 35.4 newtons plus, what was mg there? The weight of the pulley was 2 kilograms, 2 kgs times 9.8 meters per second squared. And that's going to give us wait a minute. 55 newtons. So that's 55 newtons. All right, that was 1016. 1024 reads, a uniform marble rolls down a symmetrical bowl, starting from rest at the top of the left side. The top of each side is a distance h above the bottom of the bowl. The left half of the bowl is rough enough to cause the marble to roll without slipping. But the right half has no friction because it's coated with oil. How far up the smooth side will the marble go, measured vertically from the bottom? How high would the marble go if both sides were as rough as the left side? And how do you account for the fact that the marble goes higher with friction on the right side than without friction? All right, so how we're going to do this? We're going to calculate the velocity at the bottom of the bowl. So we've got, and we're going to release it, mgh is going to be equal to, this is conservation of energy, 1/2 mv squared plus 1/2 I omega squared. So I is for a solid sphere. So this is going to be equal to 1/2 mv squared plus 1/2, and a solid sphere is 2/5 mr squared, 2/5 m, big M, r squared, omega squared, and omega is going to be v over r, so this is going to be v squared over r. So this is 1/2 mv squared plus 1/5. This is the same mr squared plus v squared over r squared. So this is going to be, these guys will cancel, and this is going to be solving for v. This is mgh. M's go. V is going to be equal to the square root of 10/7 GH. All right, that is the speed at the bottom. Let me pause and clear. All right, when it's going up with a frictionless edge, we've got from the bottom is going to be equal to 1/2 mv squared plus the k rotational. That's going to be equal to the new mgh plus k rotational, because there's nothing, if it's slick, that k rotational is not going anywhere. It's just going to keep on spinning as it goes up. So they call that h prime. So these guys go. So 1/2 v squared equals gh prime. So we'll do h prime is going to be equal to v squared over 2g. And that's going to be equal to, v squared is 10, 7. And this is gh over times 2 over g. So h prime, I'm sorry, h prime is going to be equal to 5/7. Whoa, 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 whoa. 1 minute. Let me get my algebra straight. All right, one more time. Solving for h prime. All right. H prime is going to be equal to v squared over 2g. H prime is going to be equal to 1/2g times 10/7 g. Wait a minute, there's a gh. Okay, all right, right. That's the former h. So yeah, there we go. G's cancel. The h prime is going to be equal to 5/7 h. So it's not going to go quite as high as it was, because it's not using that rotational energy to make it advance up the side of the bowl, because there's nothing for it to grab onto. So it just spins. All right. Were there friction there, it would go just as high on the other side as it on one side, on the friction side, as it came down the other side. And explain it has nothing to grip onto if there's oil on that. So it keeps on spinning and it doesn't use that to grip onto and advance it up the bowl and trade that for potential energy. It's still spinning when it reaches the top of the other bowl, of the other side of the bowl. And that was 1024. 1039 says a hollow, thin-walled sphere of mass 12 kilograms. And diameter 48 centimeters. So let's go ahead and 0.48 meters. Is rotating about an axle through its center. The angle in radians through which it turns as a function of time is given by theta sub t equals a t squared plus b t to the fourth, where a has numerical value of 1.5, so a equals 1.50, and b has numerical value of 1.10, b equals 1.10. What are the units of the constants a and b? And at time 3 seconds, find a, the angular momentum of the sphere, and b, the net torque on the sphere. Okay, now if these have to be in a, if we need an angle of, or we need a value in radians, so a's got to be radians per second squared to take care, and b's got to be radians per second to the fourth. Okay, so find the angular momentum of the sphere, and that would be L equals I omega. Omega is d theta dt. So we're going to get for that, let's see, 2 times 1.50 radians per second squared times t plus 4 times 1.10 radians per second to the fourth times t cubed. And we want to find that at some value. Let's see, find the angular momentum of the sphere and the net torque on the sphere. Okay, so yes, that is at some value, and that's at 3 seconds. So omega at 3 seconds, if you put 3 seconds here and 3 seconds cubed there, you're going to get 1.28 radians per second. No, yeah, 128 radians per second. And I of a sphere, hollow sphere, is 2/3 mr squared. So L equals I times I omega, which is 2/3 times m is 12.0 kg. R is 0.48 meters quantity squared times 128 radians per second. L is going to give us 59 kilograms, 59 kg meters squared over second. Oh. Yes. All right. T torque is dl dt. So let me clear some board space. So torque is going to be equal to I d omega dt, which is going to be equal to I times 3.00 radians per second squared times 4 times 3, 12, plus 12 times 1.1, so that's 12.12. 12.12 radians. Oh, wait, did I have, that was radians to over seconds to the fourth times t squared times I. And if you do all the math on that, you're going to get 56.1 newtons times meters. And that was 1039. And that concludes the homework for chapter 10.